let's get started. Hopefully, can you all hear me in TV land? Hopefully, a thumbs up would be great.
Yeah.
All right, thank you, Connor. All right, so I asked you for homework to do some practice. How'd that go? Anybody had any issues with it? Do we even need to cover it in class, or what do you think? I need some direction.
Yeah.
You what? You want to cover it? Okay. So we'll use this marked up over here. We'll go to whiteboard. We'll paste it. I want to paste. We'll zoom in a wee bit. Okay. So it doesn't really matter with mesh analysis as long as you keep track of things. You really, you can start at any current you want, any loop you want, it doesn't matter. So we'll just start with I1, but you could start with I2 if you prefer. So the way that we do I1 is we know the direction that we have, right? We can see I1 is in the counterclockwise, sorry, the clockwise direction. And now we start showing our voltage drops because of our current I1 flowing through there, that loop current. We're also going to do the same thing for I2, right? And what I do, just kind of as a way to make it easier for me, is I put the plus minuses on the same side where that mesh current is. So you saw the two currents, the two voltage drops I did initially. I put them to the right or below because you can hopefully see very clearly that that's the voltage drop that is occurring because I1 in that direction. When I did I2 for that center 4 ohm resistor, I have a voltage drop going plus to minus as a result of I1 in the down direction. But for I2, it goes in the opposite direction. So if you put them on the same side, it gets confusing, right? As to which one you're talking about. So I just go ahead and show that on the side where that branch current lives or that mesh current lives. If you want to use different pen colors or pencil colors, that works perfectly fine as well. But sometimes you don't want to carry around multiple pen colors. So I just suggest doing it that way. Okay. So now we're going to write mesh I1. And I'm just going to do the sum of the sum of the voltage drops are on a closed loop equals 0. So I'm not going to go the voltage raises and the voltage drops. I can see that starting over here, I've got a plus to minus voltage drop. So that's 4I1. But I also have a plus to minus voltage drop in the other direction. So that becomes minus 4I2 plus 2I1. And that becomes a plus 3 volts, right? Because in the direction of current flow, or assumed direction of current flow, that voltage, the 3 volts is dropping. And that sums to 0. For mesh I2, I'll just start again in the lower left-hand corner. That's where I like to start. I have a voltage rise of 5 volts, so that's a negative 5-volt drop. Then I have a voltage dependent source, but it's still a voltage source, so I can still just go ahead and include it just by using KVL. That becomes a minus 4I1. Who cares that it's a dependent source? It's still a voltage source. Then I have plus 4I2 in the direction, and then we have an opposite one, I1. And then my last one is here. So now I'm going to start setting up my matrices so I can go ahead and just enter the stuff in the MATLAB. And tell me if I'm going too fast on this, okay? So I have -3 and +5 is going to be equal to 6I1 minus 4I2, 4I2 minus 8I1 times, oops, I put I1s. I shouldn't have done that. I'm too ahead of myself. Times I1, I2. Any questions on how I got those? And actually I have 8 over here, right? I missed I missed this one over here, so I have two I1s there. Did I go too fast on this? So I'm going too fast?
Yeah.
Well, so one of the things you can do as an intermediate step, and this is where I combine steps, I just set this equation up so I can see that I have 4I1 plus 6I1 minus 4I2 plus 3 equals 0, right? Just kind of moving the I1 around. And then I factor out the I1s. I said 2, not 6. So that becomes 6I1 minus 4I2. And I'm going to move the 3 to the other side of the equation because when I set up in my matrices, I don't want to, I can't put the 3 term in there. I've got to move it to the other side. So I subtract it from both sides and then I get -3. That's what I have for coefficients here, here, and here. I do the same thing. So I'm moving terms around. So I have all my I1s together. Then I have my I2s together. I2 plus 4I2. And then I just keep my -5 on that side. So the next step I'm going to do is put it so that I have one single I1, one single I2, and all the knowns are going to be moved to the other side. So I have -8I1 plus 8I2 equals +5. And so those coefficients come from that last equation. Okay? And that's it. I don't have, even though I have a dependent source, did I have to write an additional equation? No. Why did I not need to write an additional equation? Normally, when we said you have dependent sources, you have to write one additional equation. I only wrote 2 mesh equations here, right? Why didn't I need to write an additional equation?
Is it because you've added the third equation into your first and second, essentially?
I don't know if I've added a third equation because I haven't really written a third equation, right?
Well, what would have been your third equation is now just integrated into your first and second equation.
Well, what would be your third equation then?
Wouldn't it be like 4I1 subtract or 4I2 subtracted by 4I1?
4I2 minus 4I1. Why would that be an additional equation? That just gets the voltage drop here, right? That has nothing to do with my dependent source. Oop, go ahead.
Would it be I1 minus I2 over 4?
I1 minus I2 over 4, is that? That's basically what Brandon just said, right? But kind of summarized it. The reason why I didn't have to write another equation is because that voltage, 4I1, is written as one of the variables that we're already solving for, right? So if that was 4 times the voltage drop across here, V2, then we would have to write another equation. But because its actual magnitude or its value is determined by multiplying a current that we're already solving for, it's not necessary to write another equation. Okay. So even though I did these this morning, you can see that there are no variables in my workspace, right? Everybody see there's no names here, no values. So if I try to type anything in, like V, it tells me there's no variable, right? So I'm going to go ahead now and enter in my I matrix is going to be equal to that R matrix, 6 minus 4, next row, minus 8, and 8, raised to the -1. And that multiplies that voltage matrix, -3, +5, and my currents become I1 is 250 milliamps, negative, and I2 is 300 75 milliamps. Those two jive. Okay. So why did I include this one here? And why did I ask you to do it for homework? The hope is that you look at this and say, it has a dependent source. It's still a voltage source. So what? It doesn't make it any more challenging. As long as I go back to my fundamental understanding of, hey, this is KVL, it is a more straightforward. Okay. Any questions on that? Was it good to go over it again? Or was it a waste of time for class? Feel like it's giving more insight perhaps if you've done it already? Okay, good. So now, how about this problem, which is kind of a drag, isn't it? And the drag is if we want to apply KVL, what is the actual voltage drop across here? Can you tell me what a voltage drop is across a 7 amp power supply? I don't think you can, right? Because the actual voltage is going to be determined based on what the rest of what's happening in the circuit. So I have no way of doing a loop I1. I mean, I can do the -7. I can do plus 7I1 minus 7I2. And now I've got to write the voltage drop across a 7 amp power supply. Can't do it, can you? Say that again. Because I've got a voltage drop here to here and here to here. Oh, 1, yes. Not a 7, thank you. But I still can't, even though I put the 7 there and was wrong, I still can't go. So I'm still stuck. So what I need to do now is somehow get that voltage drop across that 7 amp resistor from some 7 amp resistor, 7 amp current source from some other place in the circuit. Where is the other place? Any ideas? I can use the concept. Go ahead, Luke. No, because I know that this is plus to minus what? 14. But does that tell me what that plus minus voltage drop is? I would only get that if I knew what this is. So how are you going to get it? Well, if I look, this voltage drop, isn't that the same as the voltage drop there? The voltage across the 3 ohm and 1 ohm resistor. So what I do now to go ahead and solve for the voltage drop that I have here, let me erase some of this because it's getting kind of busy. To get the 7 amp and 2 ohm voltage drop, I'm going to actually steal that over there. Okay. So this is the concept of a super mesh, which really means I've got to steal the voltage from someplace else. So what I'm going to do now is I'm going to modify that, and my loop is going to become this. Okay. That's the loop that I'm going to follow to get all of the voltages, but I'm not changing the loop currents. The loop currents are still I1 and I3, right? But I no longer can take advantage of having I1 go in that really small loop. I have to combine that. So I'll do my plus minuses here because that doesn't change. And the plus minus voltage drops are based on what the loop current going through there is. And now I'm going to do loop I1. So I'm good to go with this part right here. -7 plus I1 minus I2. Now I'm over here. Now I need to get this voltage drop over here. So that becomes plus 3I3 minus 3I2. Everybody see how I got that? And then I go through my 1 ohm resistor, and that equals 0. Okay, I've closed my loop. So I'm feeling like I've got at least one valid KVL equation that I can use. Since I've closed that loop, I'm good to go. Okay. Now I'm going to do loop I2 because that's just a standard old loop approach that we do. And we have I2 minus I1 plus 2I2 plus 3I2 minus 3I3 is going to equal 0. Right? So let's check and see. And let's clean it up. We'll clean this one up over here so it looks like it's in standard form. So I have positive 7 is going to be equal to, I have 1 I1 right there, and that's it. I have negative 2I2, negative 3I2, which means negative 4I2. I have 3I3 and another 3I3. That's my first equation. My second equation is 0. I have 1 I1, and it's a negative I1. I have I2, 2I2, that's 3I2, plus another I2 is 4I2, and minus 3I3. How many equations?
2.
Question?
For loop I1, the last, resistance, would that be 1?
Oh yeah, there'd be 1, sorry. I am not in my bestness here. So that becomes 4, right? So I have 2 equations. How many unknowns?
3.
3. So I need 1 additional equation. Where can I get 1 additional equation that does not introduce a new variable? This is when you go back into your mesh approach and you said, I've got a current source in here someplace. So I know the current going through this one particular branch. So right through here is 7 amps. And that tells me I1 minus I3 is going to equal 7. Yes, did I not add them correctly? Yes, it should be 6, not 4. Looks like 61, so I have to clean it up a little more. Yeah, because I have I2 plus 2I2 is 3I2 plus 3I2 is 6I2. Now I have 3 equations. All I have to do for this last equation is 7 equals I1 plus 0 I2 plus a negative I3. 3 equations, 3 unknowns. Do you want to see how to put this in MATLAB, or you feel like you're getting sick of seeing me put it into MATLAB?
I think it's more helpful putting in the matrix on the board.
Then doing it in MATLAB? Okay, so does anybody want to see the MATLAB stuff? No? Okay. So it's already set up in standard form, so all you have to do is plug and chug. And well, I guess maybe we have to do it in this case, right? Because we don't actually have the answers. So let me go ahead, and for those of you who don't want to see that, you can just ignore for the next couple minutes. I'll do this fairly quickly. So I have my I is equal to, let's see, 1 minus 4, 4, minus 1, 6, minus 3, 1, 0, minus 1, raised to the negative 1. Multiply that by 7, 0, and 7. So I1 is 9, I2 is 2.5, and I3 is 2. Okay, and you can sanity check that because we said the current through here has to be equal to 7. We said I1 is 9 minus I3, which is 2, which is equal to 7. Okay? Questions on that? So do you ever remember being taught? I know when you said no to supernode, what about super mesh? Were you ever taught super mesh? That was a formalized approach. But what we did is we basically, so the old approach is if you have a super mesh, you open circuit your current source and then you continue the loop. But we didn't even bother with that. We just said, well, we can't get it from there. So we're going to go around it and get the voltage from somebody else. So by saying open circuit it, you're basically saying get the voltage from some other place. And so whenever you look at the concept of super mesh or super node, it really is telling you to put a short or an open so that you can find either the current or the voltage from some other place in your circuit. That's all it means. Okay, so not really super difficult, just go from there. Okay. All right, 5 minutes. Go. Let me just move this into whiteboard. Paste it in here. And okay. 5 minutes. One more minute. All right. Who's got the answer? Or answers? Anybody? Didn't have enough time or didn't know what to do? But you knew what to do? We can keep working. And then I'll tell people how perhaps I would start on this one. Because it's a little more complicated, right? Because there's a lot of stuff we need to worry about. So for this one, the way I would maybe tackle it is, I would say what I'm looking to find or what I need to find. I know I need to find I1, I2, I3, and because my dependent variable is based on not a current, so it's a new variable, I'm also going to have to find Vx, right? And so now I'm going to look at my circuit, and is there any really efficient way to solve for that? Well, oh boy, I've got a couple current sources, which is a drag, except having that 15 amp current source means I know exactly what I1 is. I don't even have to think. There's no calculations necessary. If the only mesh current that goes through my 15 amp is I1, do you need to do any mesh equations for getting I1? Know what it is. And similarly, let's see, so for Vx, that's going to be equal to 3 times I3 minus I2, right? And one other thing I know is 1/9 Vx is going to be equal to I1 minus I3, right? So I almost have all my equations there. I have 1, 2, 3, 4 unknowns and 3 equations, right? I only have to write 1 equation more, don't I? And I can write pretty much any equation. I'm going to write the easiest equation that I can see in here because I don't have any current sources. I don't have any dependent sources. I don't have any of that stuff. So I'm not even going to use the super mesh approach, which would require me to continue that I1, which doesn't really help me all that much. I'm just going to go ahead and write a loop equation for I2, which says I2 minus I1 plus 2I2 plus 3I2 minus 3I3 has to be equal to 0, doesn't it? Have I introduced any new variables? Nope. Now I have 1, 2, 3, whoops, 4 equations and 4 unknowns. So I only had to write 1 mesh equation. So did this problem seem insurmountable because you had dependent sources plus current sources when you were trying to find KVL? Is that a yes or no? We're not sure. Luke said you know how to tackle it. Were you on this track or?
I was just substituting the current source for everything. So,
Say more, you were substituting the current sources. Like, what do you mean?
like, for the 15 year,
Yep.
now
You just erased it.
but I substituted that for 2I2 plus I3.
You substituted,
Like when you're doing the equation for I1.
Yeah.
I started out by doing 2I2 plus I3. And then I did I1 minus I2. And then I substituted other current for
not sure. That's okay. It's still just KVL, right? You're still going around a loop. So make it easy. Just go around the loops. And then you're all smart, brilliant people. Why not just go ahead and look at the circuit and see, I already know a lot of this stuff. So I don't have to chunk through and write a million equations. Yes, sir.
So people that I thought that 19 DX current source going the opposite,
Going up?
it's going up, but that would mean it's going opposite the 15 amp, right?
Yeah, so you're right. This should be,
So I thought that would, that I1 would not equal 15 amp because it has the opposite current coming in from the other current source.
well, I see where you're getting at, but the problem is this is dictating you've got 15 amps through there, right? That's an ideal current source. And the only loop current that goes through there is I1. So yes, there is that current source going through there, but it could be going in this direction, right? Or it even could be a negative number. We don't know. So because you have that independent source telling you it's going to be 15 amps, that rules the roost. You're stuck at 15 amps. There's no ifs, ands, or buts about it. So now let's set it up in standard form. 15 equals I1 plus 0 I2 plus 0 I3 plus 0 Vx, right? Just setting it up so we can put it in a matrix. Our next equation, 0 equals 0 I1 minus 3 I2 plus 3 I3 minus Vx is my second equation. My third equation, 0 equals minus I1 plus 0 I2 plus 1 I3 plus 0 Vx, minus 1/9 Vx minus 1/9 Vx. And my last equation, I can see that I've got 1 I1 or negative I1. I've got I2, 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 so that is plus 6 I2 minus 3 I3 plus 0 Vx. So these are my cleaned up equations. Now, hopefully it's fairly efficient for me. And again, if you're confused, go ahead and put your variables next to the matrix you're trying to put the coefficients in. I've got 1, 0, 0, 0, 0, minus 3, 3, minus 1, minus 1, 0, 1, minus 1/9, minus 1, 6, minus 3, and 0 on my matrix. I gave you answers to that, but I'll just put this really quickly up in MATLAB so you can see, and I'll just call it my I matrix is going to be equal to, let's see, 1, 0, 0, 0, minus 3, 3, minus 1, minus 1, 0, 1, minus 1/9, and lastly, minus 1, 6, minus 3, minus 3, and 0, raised to the minus 1. And then I multiply that by 15, 0, 0, 0. Let's see, am I missing something? Yeah, right over here. I thought I put the comma, but I guess I didn't do it. So I1 is 15, which is what we thought it was going to be. I2 is 11. I3 is 17. And VX is 18. Let's check and see if that jives. I1 we knew was 15. I2 was 11. I3 is 17. And this one, we didn't even provide the answers for VX, but hopefully you can pretty quickly see how to pull out VX from that. Okay. Questions on mesh, because that's pretty much the major parts and pieces for doing mesh analysis. We pretty much examined it every which way we can, right? With dependent sources where we had to do super mesh. It's all the same thing over and over again, but sometimes you might have to apply a little bit of different information. And so that's what you hopefully will do is you'll develop expertise over time, practicing. Eventually, you'll be able to do these, pretty quickly, just by inspection almost, you'll be able to spit out some results. Okay. You can use either one, mesh or node. Most times, unless we tell you specifically, but once you get out in industry, they'll say, here, find what the answer is. You can pick which one you want. Usually, nodal analysis is the best. It's the easiest, I should say. But you may be more comfortable with mesh analysis. So if you're told, hey, give me an answer for this particular circuit, when you're out in industry, your boss isn't telling you which one to use whichever one you're more comfortable with. But I will tell you that doing mesh analysis is probably going to be more work than nodal analysis. Not 100%, but probably more work. Okay. So like in this case, which would you do? Would you do mesh or would you do nodal analysis? Well, let's see how many meshes you have. 1, 2, 3, 4. How many nodes do you have? 1, 2, 3, 4. And then again, we have our reference node. So in this case, it might, you can pick whatever you want, except if you realize that this node V1 is equal to 100 volts, you really don't need to do any mesh or nodal analysis to get that. You can write an equation for here saying V2 minus 100 divided by 8, right? If you know what the node voltage is, you can actually substitute that in right off the bat. You don't have to wait to calculate it. You can just plug it in right there. So if you recognize that when you did nodal analysis, you'd actually only have 3 equations that you need to write. So nodal would most likely be a little bit easier. Nope. Superposition. Somebody asked what was, when we talked about what supernode was, we said, what is the concept of superposition? And if you were taught, was everybody taught superposition in previous years? Why? Why were you taught that? What were you told the reason for being taught superposition?
Multiple sources.
Yep, but can't you do mesh or nodal analysis to do that? So is that what they said? You have multiple sources that you should use superposition? It's okay, you don't, this is not, you're not on the white lights and everybody's grilling you. It's more, what were you told the reason to do superposition? Because you have multiple sources. So I countered that, which is in mesh and nodal analysis, we've looked at circuits of 2, 3, 4, 5 different sources. So you don't need to do it for that, right? So what else? What other reasons were people telling you to do superposition? Other than just to say, here's superposition, let's make you do extra circuit analysis work. Maybe that's why. They probably never told you that, but. Anybody give you a reason why? That you can recall? Probably not. Because it's one of those things that are in your books, your circuit analysis books. But unless you read, kind of deeply into it, they never tell you the reason why you use superposition. The reason why you use superposition is it makes more complicated analyses much, much easier. So like I teach a senior level class in power systems, and one of the things we do is we use superposition. So we'll analyze in a very complex system with millions of different sources and loads and transmission lines and all that stuff. And if we had to do superposition for that, we'd be there all year, right? But we can solve for all the voltages in the system. And then when we put a fault on the system, the bus that fault occurs at goes to 0 volts. Well, what you can do with superposition is you can insert a voltage source in the opposite direction of what the nodal voltage is, and you force that node to be at 0 volts, which is essentially short circuiting it out, right? So superposition is there really to simplify more complicated analysis. That's the only reason why you would do it. Okay. So superposition says, if you wanted to solve for any parameter in a network, all you need to do is turn off all linearly independent sources and then add one at a time in, solve for the voltages or currents, whatever you're looking for. Then repeat the step. Make sure that supply that you just turned on now is turned back off. And then you turn on another power supply. And then you run through the paces and you see what you end up getting. And then when you're all said and done, once you've gone through all the independent power supplies, at that point, you just add your voltages or currents up, making sure you keep track of polarities, and then that'll get you your final answer. So here's the key thing. How do you turn off a linearly independent source? How do I turn off a voltage source? Short it out. Replace it with a short. Which one is it? Okay. Remember what an ideal voltage source is, right? It's a voltage in series with a resistor, right? What is the value of this resistor? If it's ideal. Infinity? How much voltage are you going to see when you add load? You would see no voltage, right? So this has to be equal to 0. When you turn off a voltage source, what do you do to the voltage? You make it equal to 0, right? So what ends up happening is you have something that looks like this. So turning off a voltage source means you're replacing it with its internal equivalent impedance only, which is a 0 ohm resistor. Current source. What is the value of R when you have an ideal current source? That's equal to infinity, right? So when you turn that off, I want to force the current out of that current source to be equal to 0. So I'm going to replace that with an open circuit, right? The only way to make a current source go to 0, because otherwise you'd be connected to something and current could be coming in. But to force that current source to 0, I replace it with an open circuit. Then I include my internal impedance, which is infinity. So I'm replacing an independent source with its internal impedance, which is either a short circuit or an open circuit. Just depends on what it is, okay? So the superposition concept is you can do it all at once, again, if you want, which is usually the easiest way to do it. Or I can turn off IA, right? Make that equal to 0, and then solve for that A matrix. Same thing, I can turn off IB and solve for the A matrix again, if you will, and then I can add it all up at the end, and that gives me my correct results. So we talked about this. The voltage or current is done by adding algebraically all those individual voltages and currents by taking those independent sources all one at a time. Here's the concept we talk about, right? A voltage source is its internal impedance, which is an open. Current source is replaced by its open, or internal equivalent impedance, which is an open circuit. And if you ever have a dependent source in there, you cannot turn that off. You have to keep analyzing the circuit with that dependent source in there. Okay. All right. So let's solve for the circuit. So what do you want to turn off first? Do you want to turn off the voltage source or the current source?
Current source.
Turn off the current source first. Okay. So our first circuit, so we'll turn off IS. We have 3, 6, 9. This is IX. How do we turn off the current source?
Open it.
Open
Open circuit.
So this is just a hanging open over there, right? So IX, because of VS, is equal to 3 volts divided by 6 plus 9 ohms, which is 3/15, which I think is 0.2 amps in the downward direction, right? That's the first step that we need to do to go ahead and do that. Now we're going to turn off our 3 volt. So let's draw the circuit that's staying in. How do we turn off an ideal voltage source? What do we do? Replace it with a short circuit. And we are solving for IX. So at this point, it's just easy to use current divider to go ahead and solve for IX. So IX is equal to 6/15 times 2, which is 12/15, which I think is 4/5. Did I do that right? Divide the numerator and denominator by 3, we get 4/5 of an amp. And again, that's in the down direction. So I total is equal to IX, I'll put because of IS over here, VS plus IX as a result of IS, which is equal to 0.2 amps in the down direction, plus 4/5 amps or 0.8 amps in the down direction, which is 1 amp total in the down direction. I will pause here. Did I go too fast? Probably went a little fast. I'll give you a minute or two to catch up.
Is that
4/5. Because it's 2 times 6, which is 12/5. I divide both the numerator and the denominator by 3. And I get those values. Trying to teach my son because he's doing a lot of fractions, multiplication and division. So what I've been teaching him is instead of going to 12/5, I say, go ahead and see if you can divide things out. Well, I know I can divide the 6 by 3. and the 5 by 3, so I'm dividing by 3 over 3, right? Or factoring that out, and it's just 1. So I end up with 2/5 times 2 over 1. And I can't do anything down, so it simplifies the fractions a lot. So if you can't see it right off, sometimes it's easier just to factor it that way. Right here. I can even zoom out a little bit, so maybe we can get the whole kit and caboodle. How's that?
If the currents were going in opposite directions, would you subtract them?
Yeah, because you're adding them algebraically, so you got one going down, one going up, so you would subtract them.
Would it matter with
Yes,
the,
yes, because our reference here shows IX going in the down direction. So if I give you an answer of IX as +1, you know, based on your schematic, that IX is going down. Correct. Yep. But if I was sneaky and I said IX is up here, then you would put a negative by 1. Luke, do you have a question?
yeah, for the first equation, what is the leftmost of the equation?
IX underscore VS as a result of VS. That's the value that you get. Another superposition? Sure. Let's see if I have another one here. Let's do it with dependent sources. Okay? It's the same approach. We'll just do it with a dependent source. So let's post here. And I've got 2 independent sources, and I'm trying to solve for V using superposition. So V, as a result of the 10-volt source, my circuit becomes plus to minus 10. 2, my current source is now open because I turned it off. 1, and I can't get rid of my dependent source. Oops, sorry. Hard to write on these sometimes. And this is my plus to minus V, and my controlling variable IX is in that direction. Okay. And so what I can do is just 1 KVL loop, right? Negative 10 plus 2IX plus IX, 1IX plus 2IX equals 0, right? So what I see is that IX, as a result of the 10-volt source, is going to be equal to 5, correct? Positive 5 amps, which means that Vx, as a result of the 10-volt source, is going to be equal to 10 volts plus the voltage drop over there, which is 5. So that's going to be equal to 0, right? There's no voltage across that 3 amp resistor because of that 10-volt source. Sure. This voltage here is 10. This current here is 2 amps as a result of just having the 10-volt source in there, right? All right. Do you see how we solved for, I said 5, this should be, that should be 5. So it's 5 amps going through there. I've got 10 volts here. This voltage plus to minus here is just a KVL loop over here, which I go up 10 and then I drop 10. So the voltage there is 0. The second circuit or the right here? No, I can, right? I can see that this voltage over here is including this current through there, which gives me a 10-volt drop. So either one is the same thing, right? Now I got to do it again. So this is going to be V as a result of the 3 amp. So I redraw my circuit. This is a short circuit. This is 2, 3 amps. This is 1. And this is 2 IX, right? So I'm going to do a nodal analysis approach here. Remember how we said with mesh or loop, you can use either one? If I can go ahead and calculate the voltage there, then I'm in pretty good shape. So I'll assume a current direction here and here. And so I've got V, we'll call this V1. V1 divided by 2 is the current going out on that left side, plus V1 minus 2IX, divide that by 1 is this current right here, and plus 3, or not plus 3, equals 3, right? So the current's out equal the current in. So that's going to equal 3. How many unknowns? 2. So I need to write one additional equation, which is the controlling variable, Ix, is going to be equal to V1 over 2. Right? But it's a negative value because Ix is going in that direction, right? That's assumed direction. So it has to be a negative V1 over 2. So at this point, Vi over 2 plus Vi over 1 minus 2. I said minus 2 and I wrote minus 3. 2 times negative Vi over 2 equals 3, right? So now I'm going to collect terms. I got Vy 1 over 2 plus V1, which is 1.5 V1. And over here, these will cancel out. So then I'm left with a positive V1. So I have 2 V1 plus V1 over 2 is 5 V1 over 2 equals 3. So V1 equals 6 over 5. And then I add them algebraically. 0 plus 6/5 is equal to the voltage. This one was a little more complicated because I had that dependent source. But it's not incredibly difficult. So that last one was kind of cool because it had dependent sources and we did mesh and nodal analysis, right? All in the same problem because we found it easier to use mesh and nodal analysis. So I'm showing you what I hope is the easier way to do it. That does not mean that this is the Paul's way is the highway. It's the way that you're most comfortable with, unless I tell you specifically, do mesh, do loop. You can use whatever you want. I will tell you, if you try to do tests or homeworks where you do a bunch of series parallel combinations, you have a high probability of making mistakes because there's just a lot of math. And when you do all those combinations, you end up losing some key information. It just disappears because you've buried you've buried a current or a voltage that you're trying to solve for. So then you got to back things out and then you got to do a bunch more work to do it. So usually it's much easier. As you saw what I did here, I didn't combine any resistors. In any of the work that I had over here, I never combined any resistors. I just did all the baseline work. It makes it much, much easier to do it that way than the other way. Questions on that? I think that was the last superposition slide. So this one even solves for Ix, but we were actually looking for voltage. So doesn't matter. All right, any questions? You ready to get into source transformations, or have you had enough material for a day? I'm not feeling a lot of energy. Are our brains full of new material?
Just a little bit.
Just a little? One of my jobs as a professor, and that's why it's really important as many people come to class, is looking around and seeing, hey, I'm smiling, I'm grooving, I'm digging this, or it's like, oh boy, seriously, we're gonna do more stuff. And as long as it's reasonable, I can always let you out of class early. Or I can keep pounding material. Although today I probably wouldn't pound material. I'm not feeling the best, so. But you can't use my poor health for a reason to get out of stuff. But I would be okay. Oh, go ahead.
I did have a question about the last, one, when you went over. The answer.
Mhm.
5v1.
5v1/2, yep. And then I just inverted and multiplied, I get v1 equals 6/5. Take the reciprocal of the 2/5 or the 5/2.
How did you get the 5v1? So they don't.
How did I get the 5v1? The 5v1/2? Because when I went over here, unless I made a mistake, v1/2 plus v1 plus v1, right? So this is 2v1/2 plus 2v1/2, which is 5v1/2, right? I felt pretty confident about that because I've been doing a lot of fractions over the summer.
No, you're right, I didn't miss that.
5th and 6th grade math, I do a lot of fractions. I don't have the heart to tell my kid, just put it in decimal, it's so much easier, but yeah, he just has to grind it out. So I felt pretty comfortable doing that. But like even you, because I screwed him up on fractions this year. I was doing stuff with fractions and I was like, I did this all wrong. Because 3 1/2 multiply by, I think it was multiplied by 2 1/4. I would just say, okay, it's 6, and then you multiply the fractions together. But 3 1/2 is 3 plus 1/2, right? So that really is 7/2, not 3 times 1/2, right? So that's I was screwing him up over that because you just don't do that. Because when I look at this, 3 1/2 to me is multiplication, right? But it's 3 plus 1/2. It's not 3 times 1/2. So, I was struggling with 5th grade math because of the the conventions we use. It's not consistent, right?
What is that called? They name.
It's called mixed numbers.
Mixed numbers and improper set.
Mhm. So I just struggled with it and had to relearn how to do fractions over the summer. All right, so I didn't hear any opposing, like, let's keep pounding material. How about I let you go 13 minutes early? More like 10 minutes because I did start class a couple minutes early, right? I'm aware of these things, so try to give you more value for your money. Anyway, any last minute questions? You have another homework assignment, hopefully you're working on. We're almost finished with chapter the second set of material. So we're grooving right along. I think I said weekly Tuesday, but we may move that depending on how far we get. But we're almost done. We probably have another couple weeks of reviewing circuit analysis and then it's all new. So we've done almost your whole DC circuit analysis in under 3 weeks. Is that a lot? I don't know. Maybe a little bit, but hopefully it's review. Anyway, questions?
No, I'm just
What's
trying
that?
to get just trying to get the pre-lab into my brain with the mesh analysis. That's all.
Okay. No, I should be all good shape, but all right. Well, have a great day, everyone, and I will see you all on Monday. Take care.
All right, take it easy, Paul. Thank you.
Thank you.
Thank you, Paul.
Thank you.
Thank you, Paul.
Take care, Connor.